Okay, good morning, everybody. We're lucky to have with us Dr. Alan Barnard, the CEO of Goldratt Research Labs. He's a leading decision scientist and the leading expert on the theory of constraints. His keynote this morning will be challenging all of us on our efforts to maximize the utilization of our assets. I'm confident that this will be quite interesting and provocative. Please welcome Dr. Alan Barnard.
Thank you very much, Steve, for the kind introduction. As Steve mentioned, the title of my presentation today is Why Maximizing the Utilization of Assets is Enemy Number One of Productivity and Profitability. It's quite a big claim, so I'm hoping to deliver an equally powerful evidence that that is in fact true, and also share with you what the alternative is. So what I'll cover today is a short introduction about my company, Goldratt Research Labs, what is needed to improve productivity and profitability, just share with you the definitions that I've used for productivity and profitability to ensure that we talk about the same thing, and then to share with you the research insights that we've gained over the past 20 years or so about why efforts to maximize resource utilization is in fact the enemy number one to improving both productivity and profitability, the P squared. And then the next part will be how to resolve the resource utilization dilemma, because you'll see that there is a clear dilemma in terms of trying to maximize the utilization of every resource versus improving the performance of the whole company or the whole organization. I'll share with you 3 case studies showing the actual results that have been achieved and the strategies that we've deployed to achieve those results, and end off with some key points to take home for you and open it up for questions. So let's start. So my company is Goldratt Research Labs. We are focused on helping organizations to make better, faster decisions when it really matters. As human beings, we make thousands of decisions every single day. It's easy to get overwhelmed. The good news is that most of those decisions don't matter, whether we are an individual or manager or business owner. But a few of them do, and getting those right or wrong can make all the difference. So helping organizations make better, faster decisions starts with 2 fundamental questions, simple questions, but important questions. The first one is, how much better can your company or organization do? And that's represented by the graph there. And there's 2 answers, only a little bit better or a lot better. What's very interesting that's come out of our research is that often big changes could have very little or small impacts, but the right changes, even though they could be very small in terms of the effort that they require, could have a huge impact. And that's what we are searching for, is what are those few small changes, low cost, low risk changes that can have a big impact on your company or organization's performance now and into the future. Once we've established that it is possible to do better, we've identified and isolated those conditions that if we could satisfy them, could allow the organization to do much better, then how best to do it? What is the simplest and fastest way? The lowest cost and lowest risk way of doing substantially better. We've had the privilege over the last decade or so to work with some of the leading Fortune 500 companies around the world, also some NGOs and government agencies. The one thing that they have in common, all of these, is the incredible and relenting pressure to keep on doing more with less in less time. And that's essentially the essence of productivity, is being able to do more with the same or less resources in less time. So if we start off by looking at how do we measure productivity and profitability, profitability is of course simple. I think there's a uniform definition of that, which is it's simply the sales revenue minus total cost divided by sales revenue. So it's a profit that you have achieved in a certain period over the sales revenue, and that gives you your profitability percentage. The higher, the better, of course. But how do we measure productivity? Well, at a company level, we can measure productivity as the output of that company, which is essentially the revenue generated, divided by the total cost, which is the input. And what we want to see is, over time, is productivity staying the same? Is it going down? Or hopefully, as a result of the actions that we've deployed, is it going up? If we are not measuring productivity at the company level, but at any functional level or a business unit level that doesn't have its own revenue, we then should be measuring the output of that function or business unit and divide that by the total cost. And essentially, we want to see the same thing at a process or function or business unit level, that what we want to see at the company level, in that the actions that we've deployed are allowing the organization or that function to increase their revenues or output faster than what it is increasing the cost. So let's have a look at what that looks like. So if the green line represents the cumulative revenue or output that we've achieved, and the red line represents the cost or the total cost, of course, the difference between those two lines would be the net profit for the organization. We can calculate the profitability and the productivity. And because those two lines are diverting apart, we want to see that, of course, profitability should be going up, and as a result, productivity should be going up. That is the picture that we want to see. We have taken actions that have resulted in us being able to grow the sales revenue or output faster than what we are growing total cost. What does this picture tell us? It shows us that we have grown revenues, we've grown the output to keep up with the demand, but we've grown cost essentially at the same rate. And as a result, profitability and productivity has not increased. It's just essentially stayed the same. In this case, we've grown revenues, we've grown the output in order to meet the demand, but as you can see, we've grown costs even faster. And as a result, both profitability and productivity has gone down. So those two last scenarios are the opposite of what we want to achieve. And yet it can be very deceiving, especially the middle one, if we are looking at just the revenues and the cost, and we see that they're growing. The revenues are growing, profitability will be staying the same. But of course, what we want is we want the revenues and output to be growing faster than what we have in increase in total cost. So now that we've got the definitions established, let's look at what this looks like in reality. This is a Fortune 500 company where the top line there, you can see that the purple is the total sales revenue. The green line is the throughput or the contribution margin that the company is making. The blue line is the operating expenses, the total fixed costs. The orange line is the total variable cost, and the black line is the net profit. Those all look very positive. They look like they are going up. Sales are growing, net profit is partially growing. But when I'm looking at productivity, where I'm dividing the throughput, which is essentially the contribution margin, the rate at which this company is generating money, if I'm dividing that as its output over the operating expenses, you can see that actually at the end of this 24-month period, despite the massive investment that had been made, the productivity has essentially stayed the same. So that's what we want to target, is we want to identify strategies where small changes can help us not just to grow the top line, but to actually grow profitability and productivity. This is another example. In this case, we've measured two forms of productivity. We've measured operational productivity, which is the throughput or gross margin divided by operating expenses over time, which is the dark green line. And the light green line is capital productivity. That's throughput or gross margin, so the rate at which you are making money divided by the rate at which you are investing money. That's a capital productivity. And you can see again, despite massive investments by the shareholders, both of those, the trends are going down and not up, despite the fact that they've been growing in absolute terms, the top line and profitability. So this is to show you that if you do not have the right measurements for productivity and profitability, it's very easy to get it wrong. So what's going on here? Why does maximizing utilization, why is that the enemy number one of both profitability and productivity? And the easiest way to show this is if we look at an effort to try and maximize the utilization of any resource. So that blue box can represent one single resource. So imagine, for example, a call center agent or a bank teller. It's one single resource. Work is arriving, that resource processes the work, and they complete the work. And the question is, what will happen as we are increasing the utilization of this resource? So as the arrival rate of the work is approaching the capacity of that resource, what is going to happen to our key performance indicators? Because we'd like to be not just efficient, but we also want to be effective. And effectiveness in this case means that the work, the customer, should not be waiting too long for this resource. This is essentially what happens to the backlog or the queue time as the utilization of that resource goes up. So if that resource can say do 10 units an hour, as soon as the arrival rate approaches 10 units an hour, the queue time or the backlog starts growing exponentially. That's essentially the queue. That's what we see in traffic jams when suddenly the capacity of the road is just crosses that threshold of about 80%, and suddenly you've got bumper to bumper traffic. And whereas normally it might have taken you half an hour to travel the 30 miles at 60 miles an hour, suddenly that same journey of half an hour could take you 3 hours. What happened? You just went over that threshold where there's simply not enough protective capacity or catch-up capacity to deal with the randomness and the arrival rate. And of course, what happens is your reliability is dropping exponentially as well, decaying as well. So initially, it's very easy. Up to about 80% utilization, it would be easy to make reliable commitments regarding of how long it would take you to complete a project or to process this customer or to deliver a specific product that you are making. At the same time, what's really interesting is to observe what's happening to the throughput or the output of this resource. Initially, it keeps on climbing. So as you're increasing the amount of customers or work that's arriving, initially the resource is coping with it and the throughput is actually going up. But as soon as you get in this sort of what we call the chaos zone, you are in real trouble, because now this resource is stopping and changing, stopping and starting, and suddenly the throughput rates are going up. And yet, what's the mistake that we make is up to that point of about 80%, we think we have lots of time. There's no reason to be concerned. If we had predicted what would happen to our queue times, what would happen to our reliability, what would happen to throughput, those are the dotted lines that I've shown there. And yet suddenly just a small increase, somebody getting a customer on board, even though they might only be 5% of total sales, can push this over the thread. Or I have 10 resources that I'm deploying to provide a service to maybe a construction project or building that I'm maintaining. And the workload on those resources just exceeds this threshold of around 80 to 90%. And suddenly the work is now waiting for resources. And as the workload increases, the queue length or the backlog will increase exponentially and the reliability will decay exponentially. To give you a practical example of what this relates to is I want you to think about a case where you are asked to complete a one-day task, something that under normal circumstances should take you 1 day to do. But you are asked to make a commitment. How long is it actually going to take you to complete this one-day task? And of course, the right answer is, well, it depends. If you are not busy at all and you can start immediately, the one-day task should take you 1 day. But what if you're already 50% busy? It means that that 1 day represents half of the work that you already have. So you first have to go through the work that you've already committed to, and then you can start the task. So it will take you 2 days to complete. But what if you're already 75% busy? Suddenly that one day is 25% of what you already have loaded. So it will take you 4 days to complete. At 90% busy, 10 days to complete. At 99% busy, it'll take you 100 days to complete that one-day task. And that's a clear representation of what happens to this exponential growth. And that is true not just for a single resource, for us, for example, but it's true for a whole network of resources that are dependent on each other, that are completing complex construction projects, complex service functions, or production functions. It doesn't matter what's sitting in that blue box. As soon as it crosses this point, this threshold of utilization, suddenly all hell will break loose. And essentially it triggers a vicious cycle. We initially overcommitted or wasted capacity by doing stuff that we shouldn't be doing. That then causes this resource to become a bottleneck, a backlog forms, and there's more and more pressure to overcommit even further and produce even more stuff in order to catch up. And that's a very difficult, vicious cycle to get out of. The only way to get out of it is to find a way to go back to the sort of edge of chaos zone, like I said, where you have not overloaded that resource too much by trying to maximize its utilization. Just go back, and the quick way of checking is what happens to my backlog. So reduce the demand that we've committed to and see what happens. Reduce it further, and as soon as I start seeing, and that's the good news, is as fast as the backlog can grow, the equal speed that it can go down by just small changes in the amount of work that I've committed to deliver. So if 5% took it over that threshold, just not committing to 5% less will get the backlog down. So that's just a quick thing of showing you what happens when we are trying to maximize the utilization of any resource or set of resources. We overcommit that resource. Inadvertently, we cross over this threshold, and suddenly everything in the system is now waiting for this resource or set of resources. So how does this look like when we don't have one resource, but a set of resources that are connected, that are all required in order to deliver, for example, a service or to produce a product or to complete a project? And I want to show a small example. It's called a dice game. And the dice game is basically 5 resources or processes, and the output of each of those are represented by the throw of a dice. So A can complete anything between 1 and 6 units of work per day with an average of 3.5. And the same with all the other processes. And the question is, what would you commit to be able to achieve after, say, 20 days? Well, if each resource or process can complete 3.5 per day on average, and we work for 20 days, then we should be able to get 70. And I can now develop a financial model around that to say, for example, if I was paid $1,000 for every piece of work or widget that I complete or project that I complete, my revenues will be 75,000. Maybe my variable cost is 50%, and my operating expenses is 21,000. So I'll deliver a healthy profit of 14,000 or 20%. Of course, for anybody that's worked a little bit, you're not going to commit to the full number. So you might negotiate down and say, I feel comfortable, just in case there's some problems, I feel comfortable in committing to 60 units of work out of that. That could be 60 projects, 60 maintenance jobs, etc. And what will happen is I'm still delivering a healthy profit of 15%. But now let's see what happens when we actually run this simulation game. People are shocked to find out that the actual output is about half of what they thought the theoretical number would be. They get out only 35. Why is that? Simple, because when A produces only 1, it was unlucky to throw a 1. B only gets a 1, and C only gets a 1. So it doesn't matter how much B, C, D, or E was capable of doing that day, because they only got 1, they could only deliver 1. And even if A, B, C, D, all of them got the maximum performance, they all got 6s that day. If E only produced 1, only 1 will come out. And as a result, you get much, much less out than what you expected. And this is what we often see happens with interdependency and variability. These systems perform at a much lower rate than what we expect. Now, the question is, of course, that translates massively negatively into financial performance. A company that we thought, or department, service department that might be a profit center that we thought would deliver a healthy profit suddenly is losing money. Now, the question is, if you want to get 60, how are you going to do it? Well, if you got 35 out on average and you have to do about 60, that's a commitment that you've made. The simplest option is, of course, to double up. But that will cost a huge amount of money. And even if you had the money, it would take a long time. Is there another way, very counterintuitive way of getting close to 60? And this is one of the insights that we've gained from theory of constraints, is that what if I created a bottleneck? Because at the moment, I've got a balanced system where the bottleneck is moving every day. What if I created a stable system, and a stable system has one bottleneck, not 5 bottlenecks? And the way I'm doing that is by simply preventing C to throw a 6. I'm limiting it to produce only between 1 and 5. And as a result, its average would drop to 3. Now, the question is, if I take capacity away from one of the resources, what does your intuition say would happen to the output? We're already getting less than what we expected. Probably we'll get even less. No, we'll get more. And here's why. By leaving the capacity of A and B, D and E as still on average be able to do 3.5, A and B can build up a buffer of work in front of C because they can go faster. And that buffer of work will make sure that C is never starved of work. D and E can also go faster than C. So they can always make sure that that space behind C is always empty, so that C is never blocked. And if C is never starved and never blocked, then the capacity of the system will equal the capacity of the bottleneck. So if C on average is doing three a day, and you run it for 20 days, and C is almost never starved or never blocked of work, suddenly you're getting close to 60 without adding capacity, just by limiting the rate at which C is doing in order to turn it into a bottleneck. And now I can use that capacity to make commitments to not just my customers, but also to shareholders. So that's a very simple but quite counterintuitive way, that as soon as you realize you're in these chaos conditions where you're getting much less out, everything is taking much longer than you expect, how can you get back into that sort of edge of chaos zone without jumping all the way back to stable? Is just to make sure that you have one bottleneck and that you're controlling the release of work to the rate at which that bottleneck can process, and you have a buffer in front and behind it to make sure it's never starved or never blocked. So that's just a quick summary of why resource utilization, trying to maximize it, can cause a massive drop in profitability and productivity. But there's, of course, I mentioned the dilemma here. So what's the dilemma? If your current operational and financial performance is still below expectation, like what we show now, you're getting about 60% of what you expected. What will be the pressure? The pressure will be to have enough of everything. Make sure you have enough headcount, enough equipment, enough buffer stocks. Make sure you have enough to meet the commitments. But there's also pressure to get by on a bare minimum. Bare minimum headcount, equipment, buffer stocks. Be as efficient as possible. Each of these options have got an upside. Having enough of everything means that you'll protect and improve sales. Getting by on a bare minimum will mean that you are showing that you're making efforts to control and reduce cost and improve your cash flow and productivity. But they also have a perceived downside. Having enough of everything might end up increasing your cost per unit, or not achieving the benchmarks that your headquarters have set for you, and trying to continuously getting by on the bare minimum, living from hand to mouth, will mean constant firefighting as the bottlenecks are moving, and conflicts between what is good for the part versus what's good for the system. Either of those are bad, because it means that you will be blamed for not achieving your targets. So how do you resolve this conflict? The little diagrams that I put in here, the right-hand one is representing a mode of getting by on the bare minimum. You want to be able to commit to 10, then each of those resources should be able to do 10. Or you commit to 10, but then upstream should be able to do a little bit more, downstream should be able to do a little bit more. But is that inefficient? Let's look at the numbers here, because what we want to do is to challenge the assumption that those resources A and B, D and E, that will now be idle from time to time to ensure that they don't become the bottleneck, that's not a very inefficient way of running. So let's just say that our asset OEE here are 90% in each case. So each of those assets, those processes or resources have an availability of 90%. And that the total cost for having enough of everything is $60. That's adding the 10 plus the 12 plus the 13 plus 12 plus 13, which represents that bit of extra capacity. That gives me $60, whereas the other one is 10, 10, 10, 10, 10. That gives me only $50. What will be the output of the first unbalanced system versus the second one? Well, the first one is going to do basically 9 and not 10. Why 9? Because C is available 90% of the time. And if it's never starved or never blocked, it will get 90% times 10, its theoretical capacity, and it will get 9 out. But as we know from probabilities add up. So if it's balanced, it's going to go 0.9 times 0.9 times 0.9 times by the 10, and that gives you about 6. So you're going to get 6 out rather than the expected 10, whereas in the first round, you're going to get 9 out rather than 10. And if you then divide that by your total cost, you can see that the one that we thought was the least efficient because its total cost was the highest is in fact giving you the smallest cost per unit of work completed of $6.6 compared to $8.33. Something very counterintuitive, something that we thought that by trying to utilize all the resources, keep everything busy, that's the most efficient way. No, it's the least efficient way, because even though the total cost might be the lowest, the output is dramatically lower than the unbalanced system. So this, of course, is a theoretical exercise. What I want to show you is a few case studies of what this looks like when we apply this to a complete supply chain, for example. Here's 2 supply chains, a mining supply chain that we modeled, created a simulation model. The top one is modeling it with a push methodology, where the mine is trying to maximize its utilization by trying to produce as much ore as possible and pushing that downstream onto the process plant, through the trucks, to the trains, to the ports. Whereas the lower level one is a pull-based, where the mine is only producing what customers have bought. So top one, push, is essentially sell whatever you can produce. Pull is only produce what you've sold. Which one will give you the highest profitability? And then the results are quite staggering when we compare it. Counterintuitively, the one that feels least efficient, where it's going to cause the mines and the trucks and the process plant and the trains from time to time to stand idle because there was no committed contracts to deliver, is actually the one that dramatically has the higher profitability. So for push environment, profitability is 11% compared to pull 22%. ROI is 18% compared to 41%. Due date performance, which is represented by those color bars, black means that I'm late on either a spot market or a contract sale. You can see the pull, which is the left-hand side, is dramatically more than the pull, which is the right-hand side. So dramatic improvement in due date performance. The middle section there of the average daily output, pull on average is producing much more if we measure output as output sold rather than just output produced by the mine. And the cost per ton have gone down from $115 a ton for the push environment to $98 per ton. And then an interesting measurement is the amount of activities that are demanding the management attention in a push versus a pull mode has gone down from 24 things that demand your attention per day to three events per day, much more stable, much easier to manage. And I'm following this up with the real results of this mine that we simulated to prove over a 5-year period what actually happened. One of the mines that was operating on push, the budget for identical mines was around a 22% net profit. The actual achieved over that time period was only 9%. 59% below what was expected, whereas the one that was operating on pull with the same target actually achieved the target. And you can see also how much the cost, as per the simulation model, we predicted a dramatic reduction in the cost per ton, which shows you how robust this mine will be to withstand the downturn in the market when commodity prices go down. Of course, it's much better to have a mine that can produce at $98 per ton than one that has to produce at $115 per ton. So that's on the mining side. We also have another example here, which is a model that we developed for an aircraft maintenance depot. The planes on the left-hand side is about 100 planes. They arrive based on the maintenance schedule. They go into the depot, they get disassembled, they then get inspected, they go into queue for repair and assembly, they then get tested, and finally, if they pass the test, they go back into operations. And we modeled this first, and then we checked what would happen in real life. But the same thing is true. The one strategy is to try and maximize the utilization by getting the planes, as soon as they arrive, immediately push them into to the depot to try and keep all the crew busy inside of that depot. And that, of course, because we're measuring their utilization, to try and keep them all busy, they're going to be multitasking, switching tasks from time to time. This was the results that happened. So round one, which is a round that we ran without any variability, we called it perfect world maintenance. You can see the fleet availability there was 72%. So of that 100 planes, about 72 of them was available for operational duties at any point in time. The average cost was predicted at about $1 million per maintenance job. This is what happened if we ran it in real world maintenance, like that dice game where we just introduced variability in demand and supply. So demand variability would be maybe they give you 24 planes to maintain a year, so you assume 2 per month. Demand variability means that sometimes only 1 arrives, but other times 3 or 4 arrives. On the supply variability, the parts that you order, they quote you 30 days. In perfect world, they always arrive 30 days. In real world, sometimes they arrive in 45 days, sometimes they arrive in 20 days. But the means are the same, but you can see a dramatic drop in fleet availability going down from 72% to 59%. That's essentially 13 planes that have been taken out of operations and they are stuck in a depot because you're trying to maximize the utilization of the crew inside of the depot rather than controlling the release. And the cost has gone from 1 million to almost 1.2 million, a 20% increase in the committed cost. What would happen if we synchronize operations inside of the depot? We don't try to maximize the resource utilization, but we are controlling the release of the planes into the system based on the capacity of the bottleneck, which in this case would be the assembly bay. So it's almost like what we've done for the dice game. We don't push everything as fast as possible into it, but we're controlling it slowly and controlling it based on the number of assembly days. Just that action got our fleet availability up to 65%. And the cost down to 1.1 million. That's a 10% saving. And then when we synchronize the full supply chain, so we also feed back what the actual demand is that we are working on, what's the actual planes that are coming in, and we're sharing that with our suppliers so they don't keep on shipping spare parts based on the forecast that we gave them at the beginning of the year, but they are dynamically changing those stock levels based on what's really happening. We can get back almost to perfect world maintenance. And those are the direct comparisons that you see for fleet availability for the 4 scenarios: perfect world, real world, depot synchronization, synchronizing the work to the capacity rather than trying to maximize the capacity of every resource, and then synchronizing the whole supply chain. So dramatic improvement in results. So some key points to take home here is I want to leave you with this thing. What are the highest leverage opportunities managers can work on to improve productivity, to improve profitability and ROI? It is not to try and maximize the utilization of the resources that are under your control. The first one that by far gives you the biggest impact, the highest leverage, is if there's anything that you can do to contribute to increase your revenues for your company or your organization, by getting the average price to go up, either by reducing discounts or by charging premiums to those markets that might be time sensitive and not price sensitive. So maybe in a maintenance environment, you are supplying a service, you have a standard price that's quoted, you try to give them a fast service, but from time to time, a client might have an emergency. If you could charge a premium on supplying them with that emergency, you will increase your average selling price. And I'll show you now the massive leverage that you can get for every 1% increase in the average selling price for your company. The second highest leverage is if you can increase sales revenue by preventing lost sales, by making sure that you don't have shortages or that you don't have poor due date performance, that you haven't overcommitted. And I'll show you again the same here. What's the leverage of just reducing lost sales by just 1%? How much will that increase my productivity and profitability by? Next would be to reduce variable cost and working capital, essentially preventing overpurchasing. In this time, for example, of this pandemic that we're facing, this is critical, as you don't want to be cutting costs that are needed in order to provide the service that is required to keep your customers. You want to identify what are those things that you can stop doing without impacting your sales, without impacting your ability to meet the demand that's placed on your department. Of course, there's two other strategies. I include them as the last one because for the company to win, somebody has to lose. You could reduce variable cost when we demand a reduction in purchase prices, but that means your supplier loses. You can also reduce your operating expenses when you reduce salaries or even lay off people. That means that the employees lose. Now, I'm not saying never to do that, but only to do that when you've already exhausted the other options. So let's look at the numbers. A simple financial statement here, a company that's doing, say, 100 million in sales, and they've got currently around 5 million in net profit, so about 5% net profit. What I've done here is I've simulated or modeled what would be the impact of just a 1% improvement in each of those 5 factors. So if we can increase the average selling price by just 1%, it means our sales will go from 100 to 101. Variable cost won't go up. Operating expenses won't go up. So that whole 1 million will drop to the bottom line and will take my net profit from 5 to 6. That's a 20% increase in net profit for 1% increase in the average selling price, which we can achieve, as I mentioned, just by reducing discounts or by maybe charging premiums for customers that are time sensitive. So that 1 to 20x is by far the biggest leverage. So as a manager, whether you're working in maintenance or in HR or in operations or in project management or you're in sales or marketing, whatever you can do to help to increase the average selling price has a massive impact on your net profit. The second one is reducing sales by reducing lost sales. If we could do that by just 1% without increasing OPEX. So of course, we'll have to pay the variable cost, which in this case is about 40%. So of that 1 million that we'll get an additional lost sales, if we could have prevented the lost sale by preventing a shortage or poor due date performance, 0.6 or 600,000 would go to my bottom line. So that's an increase in my net profit of 5 to 5.6, which is 12% increase. Still massive leverage. For every 1% reducing lost sales, I'm getting a 12% increase in net profit. Over purchasing will give me about 8%, reducing that because I'm only reducing my variable cost. Reducing the purchase price will have the same impact of about 8%. Reducing operating expenses by 1% will impact only my direct operating expenses, which in this case is only about 10% of my sales. So 1% on 10%, that will give me the 1%. So that will translate into 2% reduction or improvement in net profit compared to 20%. And it's amazing how companies almost immediately jump to 4 and 5 as if that's the only options available. So if we just add 1 and 2 and 3, so if we got 1% from each of those, we'll increase our net profit by 40% just by getting 1%. Imagine if you could increase your average selling price by maybe a few percent, 5%. You could reduce your lost sales by 5%. That is by far the biggest leverage that's out there, and especially true in this case. Of course, 4 and 5 is always there if you have to do it, but they should be done as the last option. So the last point is, as I mentioned when we started this, there's a real dilemma, is that what is going to happen next with our performance? It's stagnated. You're not achieving the results that you're expecting. There's a lot of fear and anxiety now in terms of what the shape of the recovery will be. Are we going to end up at the same level as before, but it will just take time? Are we ended up much worse or much better? If there is a demand, we will have pressure to start building up the resources again, have enough of everything. How do we avoid this conflict? Is realizing that the way to control and reduce costs, the way to improve productivity is to have enough of everything. Not too little, not too much. So the key point here, be careful. The goal of the company is not to maximize the utilization of its resources. The goal of the company is to grow sales and keep on growing sales faster than what it's growing costs. And to have enough buffers to make sure that you can fully meet the demand. Having enough can dramatically increase both, but that means not too little, but also not too much. Now, how do I know for any resource if I have too little or too much? And a very simple heuristic that you can apply, a kind of a rule of thumb, is just monitor the backlog. Start checking the inbox, the equivalent of the inbox of work waiting for any resource, and monitor the backlog. Say we expect 1 or 2 days maybe of work to be waiting there. But when that backlog is growing, and especially if it's growing fast, then that's a warning sign that you have too little capacity. You have too little buffer. You need to add more. When there's no backlog, or the backlog is constantly dropping, then probably you have too much of that resource, and you can safely reduce the capacity or the number of those resources without impacting the top line. And then the last part here is to implement a productivity measurement. As I mentioned, many companies are implementing product or measuring productivity in the wrong way. They're measuring it as an efficiency or local efficiency. For example, the tons produced per head count or something. And then, of course, it artificially increases the productivity if I just reduce the head count. That's just playing game with measurement. A measurement that you can't cheat on is this throughput over operating expenses or gross margin over operating expenses for company. And if it's a service function, measuring the output over the total cost or the quality throughput over the operating expenses is the way to measure productivity. And that will show you very clearly whether the actions that you are taking, is it actually improving the productivity of your department that should translate into increasing the profitability of the company. And that's where I'll leave it today, and I'll open it up for any questions.
Alan, that's great. What a great presentation. Very, very interesting. I think one of the takeaways is that we should maybe go to a 4-day work week, because it seems like that might be a
exactly.
good value, and a popular one too, I'm sure.
Yes,
I'm sure.
Yes, and that's in fact the simplest way to prevent you from going over that 80% threshold, right, for anybody. It's a great observation.
Yeah. Yeah.
In fact, that's one of the recommendations that we work in, whether it's in the factory or service department, is to say, make your commitments on 80%. So, if you're running your factory 5 days, only commit to 4 days and keep that Friday as a buffer, right?
Sure.
So that you can catch up when you fall behind. And if you had a great week, then you have flexibility. Do I pull Monday's work forward and do it now, or do I give people off? Do I use the time for maintenance or to catch up on some other stuff? Great observation.
Yeah, no, it's very, very compelling. I must say, I think there's a lot to be taken out of this, and it's an eye opener, because it's so counterintuitive to what we would normally think are the right decisions to make. So
yes.
Very, very insightful. Thank you so much for this thought-provoking presentation.